It's a great pleasure to have the former organizer for 4 years, I think, Robert Bliss, who will talk about modular arithmetic with trinomial moduli. As usual, please mute yourself unless you have a question or comment. Thank you.
Okay, thank you for the invitation, Doron, and please unmute yourself if you're laughing at one of my jokes. That would be much appreciated. So it's always a pleasure to be back at the experimental seminar, normally listening to a talk, but today giving one. It's a special privilege today because of a nice coincidence. Eugene, do you know what happened a year ago today? Or a year ago, almost today?
Oh yeah, it was my presentation probably, no?
Exactly right. A year ago, on April 25th, Eugene, in this very seminar, gave a talk on ideas to accelerate the Chinese remainder theorem. And I was so impressed and I liked the idea that I sent him an email and asked, I had some ideas on how he could contribute. And it turns out all those ideas were wrong and bad. But over the past year, we've been able to make some improvements, and that's what I'm going to talk about today. So I'm happy to be back reporting on something that happened in our seminar a year ago.
And in a year, another year, you're going to do even better.
Yeah, maybe even on the same project. We'll see how long it takes us to finish. Okay, so I want to get everyone in the right headspace for the talk. I don't know that everyone has the same background, so I just want to begin by talking about some modular inverses. So some simple computations. I want to show you how to invert this number here. I'm going to invert 2 to the 5 minus 2 plus 1, which is also known as 31. And I'm going to invert it mod 2 to the 5 minus 2 cubed plus 1, also known as 27, I believe. It turns out that this inverse is -4. Normally, when someone says modular inverse, they mean the one with the positive representation, but I'll allow negative representations here. That's fine. Okay, there's nothing special about this inverse. This is just some modular inverse. But what's kind of interesting is that if you take these exponents and you double them, it's still true. You replace the 5 with a 10, you replace the 1 with a 2, the 2 with a 4, and so on, and this modular inverse is still true. No need to recompute anything at all. So what do you think happens when you triple the exponents?
It has to be even, right? It's the freshman's dream.
What has to be even, do you mean? Do you mean the inverse?
Doubling all the exponents. You can keep doubling and redoubling, but you can't multiply by 3. I'm just guessing.
Just guessing, okay. That's a good guess. Any other guesses?
Well, it looks like you're working in a polynomial ring. And so this is a field of some kind.
Yeah, I know the answers, but I will keep it.
Yeah, Neil is onto some things, but it turns out that for some special reasons, you can triple the exponents here, in fact. You can double the exponents, you can triple them, and it's still true. In fact, you can quadruple them. I mean, quadrupling is like doubling twice, so that's not so crazy. But yeah, you can double, triple, quadruple. In fact, you can take this identity and multiply the exponents by anything, and it's still true. And the reason for this, as Neil suggested, is actually for some polynomial reason. So if you want to prove this fact, you don't really need to do any number theory, any tinkering around with these powers of 2. You just have to write down one polynomial identity. So here's what the identity is. Let me explain where it comes from. So you start off with the 2 numbers we began with, 2 to the 5 minus 2 plus 1. And you replace the 2's that you saw with x's. So instead of 2 to the 5, you have x to the 5. Instead of 2 to the 1, you have x, so on and so forth. And then you run the extended GCD algorithm on the 2 polynomials, and you get an identity that looks like this, Bezo's identity. If you plug in a power of 2 in for x, that tells you immediately that the 2 numbers in red have to be relatively prime, and it tells you how to read off the inverse of one mod the other. And that is how you prove this identity right here. In fact, this also proves the companion identity, where you can take the inverse of the other one, mod the first one, instead of what we did, but we only said it one way here. So there's this nice fact that comes from writing down a single polynomial identity, and the immediate thought you should have is maybe this applies to other situations. So let me show you another one. So here we're going to do the same setup. Now we have some different powers of 2. Now we have 2 to the 6 minus 2 squared plus 1, and we're inverting mod something else. So what do you think should happen when we double the exponents now?
The same as before.
Same as before. That's a good guess. Unfortunately, it's wrong.
Right.
It turns out when you double the exponents here, the numbers that you get aren't even relatively prime anymore. They're both divisible by 7. Well, okay, maybe that was a little accident. Maybe if you triple the exponents, then you get back to something nice. And it turns out that if you triple the exponents, they are relatively prime again. This annoying 7 goes away, but the inverse is just completely different than it was before. You do not just multiply the exponents in the inverse by 3. It actually expands, and you get more terms than you did before. So there's not really much of a pattern here for this case, if you want to multiply these exponents. Now you might ask, what went wrong exactly? Because in the argument that we had before, it didn't seem like we really used that much other than some polynomial identity. And in fact, you can write down the exact or similar and analogous polynomial identity here for this case. So if you write down the same polynomials as you did before, and you run the GCD algorithm on them, you get another identity. And you can plug powers of 2 into this identity. But the problem is on the right-hand side now, you have a 7 instead of a 1. And we didn't use much number theory, but we did use the fact that there was a 1 on the right-hand side. And the fact that there's a 7 opens you up to the possibility that they might not be relatively prime. They might both be divisible by 7. Even if they are relatively prime, now you can't really read off the modular inverses like you could before. You have to be able to invert 7, and that may or may not have nice patterns. In this case, we see it kind of breaks down immediately. So we're done because there's a 7 on the right-hand side.
Robert?
Yes.
Something. Here on the very first line, in the module, this exponent 5, what is its relation to the exponent 2 in 2 to the 6 minus 2 to the square? Like, why do we start with this module exactly?
I picked them completely arbitrarily. There was nothing special about them other than they were smaller than the highest one. So 5 is smaller than 6 and 2 is smaller than 6. It's just an example that sometimes you get nice inverses and sometimes you don't, depending on what the exponents are exactly.
Okay. Thanks.
So let me draw those differences out a little more. From a certain perspective, we started off with 2 pairs of polynomials. The first pair of polynomials, when we plugged in powers of 2, we got good inverse patterns with respect to each other. In the second pair of polynomials, we got bad inverse patterns, in that there weren't always inverses, or the inverses grew in size, unlike in the first one. And the question is, what's the difference between these 2 pairs? What separates them? And the thing that separates them is on the right-hand side of the GCD identity. You got a 1 versus a 7. That's what separates them. But is there some way to understand what would appear on the right-hand side by looking at the 2 polynomials? And the answer is yes. If you know what a resultant is, what separates these 2 pairs is the value of their resultant. So the resultant of the first 2 polynomials is 1. The resultant of the second 2 polynomials is 7. And that's kind of how you can predict, in a way, what will appear on the right-hand side. That's great if you know what a resultant is. If you don't know what a resultant is, let me very quickly explain what they are. So resultants are a bit like determinants in a way that I'll get to. They're defined as follows. If you have 2 monic polynomials, let's call them f and g, then what you do is you take all the roots of f and all the roots of g, and you form all of the pairwise differences in that order, root of f minus root of g. You don't double count for orders to subtract. Then you multiply all of these pairwise differences together. And then there's a plus or minus sign out front that depends on the degree of f and g, but we don't really care. So I'm just going to write plus or minus because it's not relevant. If you think about this definition for a little bit, you see that you can think of it as another way. You can also compute the resultant by taking all the roots of f and plugging them into g, and then multiplying all of those values together. Or the other way, you can take all the roots of g and plug them into f and multiply all of those values together. again, with some plus or minus depending on exact circumstances on the ground. There are some important facts about resultants you should know. The first is that you can compute them without knowing any roots, despite what the definition here tells you. It's an amazing fact that resultants happen to equal the determinant of some matrix whose entries are just coefficients of the polynomials that you're working with. So no need to factor polynomials or find their roots or anything. You just compute.
It is due to my hero Sylvester, J.J. Sylvester, I think.
Yes, this is it's the determinant of the Sylvester matrix of F and G. Exactly right. And then based on what I just said, there's another nice fact, which is that the resultant of two integer coefficient polynomials is again an integer, which is again not obvious from the definition because you have to do things with the roots, but it turns out it's not anything disgusting. It's just some integer that you can compute with a determinant. And then finally, the sense in which resultants are like determinants is that a resultant is zero if and only if F have a common root over some field extension or a common irreducible factor over the rationals, for example, something like that. In the same way that a determinant being zero tells you when columns or rows of a matrix would be linearly dependent, this tells you when two polynomials have some common factor. Okay, great. Now everyone knows everything they need to know about resultants for the most part. So recap, let me go back to what I just said now that we're on the same page. We had two pairs of polynomials. One of them had a resultant of 1, and one of them had a resultant of 7. It turns out that what divides these two cases is whether or not the resultant is a power of 2. So if you try and come up with a sequence of modular inverses like we did in the first two slides, this will be nice provided that the resultant of the polynomials is plus or minus a power of 2. So you could be a power of 2 or negative a power of 2. Either one's fine. If you're not a power of 2, you're divisible by any odd prime or anything like that, then this will not be nice. You will have problems. So I can avoid saying plus or minus, your resultant is plus or minus the power of 2 for the rest of the talk. I'm going to introduce a new phrase here. I'm going to say that two polynomials dyadically resolve if their resultant is plus or minus a power of 2 or a signed power of 2. That way I don't have to keep mumbling through the resultant thing. So this is the important dividing line, whether or not your resultant is a power of 2. All right, now let me tell you a little bit about the original motivation, what happened a year ago. So you may already know this, but in case you don't, let me tell you now. If you ever ask a computer algebra system to do some computation for you, there's a decent chance that somewhere under the hood, along the way, it's doing some modular arithmetic coupled with the Chinese remainder theorem to speed up its calculations, even though what you asked might not have anything to do with modular arithmetic on its own. You can speed up computations this way. And the basic idea is rather than computing one big thing that you asked for, you reduce all of your inputs modulo several relatively prime numbers, you do all your calculations with the residues, and then you reconstruct the result with the Chinese remainder theorem. And oftentimes it's better to do many small things and then reconstruct rather than doing one big thing. You normally get some speed up, in certain circumstances anyway.
Also, you can do parallel computing with many computers.
And you can do parallel computing, which reduces even some of the cost of doing many small things. You're kind of only doing a small number of small things, actually, because all of the residues work independently. That's exactly right. So there's a price that you pay when you do this, though. You don't get to just work on the small things for free. You have to take your numbers, whatever you're working on, and reduce it modulo these relatively prime numbers. And then once you're done computing the answer, you have to reconstruct your actual answer using the Chinese remainder theorem. And that reduction and then reconstruction is some overhead costs associated with this. Things that you have to pay that aren't even really working on your problem. They're working on some accounting to get your answer right. So a common game that you play is asking, can you somehow pick moduli in a way that minimizes these costs, that makes reduction fast, or that makes reconstruction fast? Something along these lines, so that you can really get the full benefits out of the approach. So about a year ago, in a talk at this seminar, it was proposed that we think about moduli that look like this, what I'll call trinomial moduli. These are moduli of the form 2 to the n minus 2 to the k plus 1, where you fix the degree, the leading exponent n, and you allow the middle one to vary. These moduli have various nice properties. First of all, they have a nice binary expansion that makes the reduction step fairly straightforward. They also have the property that if you pick multiple of them, they'll all have roughly the same order of magnitude. So if you're doing parallel computing, you can distribute the workload evenly. And as we saw in the beginning, sometimes they even have nice modular inverse properties, which is not typically guaranteed in this method. So they have some desirable things, but there were some basic questions left over after the talk a year ago. It was only the sort of the beginning of an exploratory project. And the basic questions were something along these lines. So the first question was, how would you know in advance when two trinomial moduli are relatively prime and have good inverses, meaning that the modular inverses behave the way that we saw in the first two slides, that you can kind of scale them up and everything. You don't have to recompute modular inverses. Of course, if you have two specific ones, maybe you could just check with some simple program. But the idea is, how do you predict in advance which ones will have this behavior or not have this behavior? The second question was, how is it even possible to get arbitrarily large sets of these moduli that have this behavior pairwise, meaning if you pick any two of them from your set, they'll be relatively prime and have good inverse behavior? Because the Chinese remainder theorem is typically made better by having more moduli. Is there some theoretical limit to how many of these moduli you can pick at once? How far do you have to go to find them? And then finally, how do you find these large sets if they exist at all? Just theoretically knowing that they're out there isn't much good if we can't find them and use them somehow. So this is what we're updating everyone on today, the work of the past year and trying to answer some of these questions. And the first thing that we learned in the past year is that it's really better to not think about these moduli themselves, as in these specific powers of 2. It's much better to think about the underlying polynomials instead. So really what we want to ask is all the same questions, but translated to be about polynomials instead of integers. So if you have two actual trinomials, as in polynomials with 3 terms, when do they dyadically resolve, meaning the resultants plus or minus the power of 2? Are there arbitrarily large sets of dyadically resolving trinomials, and how could we find those sets if they exist? So that's the basic idea. Rather than thinking about the numbers, we'll think about the polynomials. Okay. Now, there's a helpful framework to think about questions like this. If you kind of take a step back, what we're really saying here is we have certain objects, trinomials. We have a relation on these objects, and we want to know, can we find sets where everything in the set is related to each other, pairwise? Well, if you think about it, you realize that you're actually asking a question about a certain graph. Specifically, what I just said, you're asking about complete subgraphs of a certain graph. So let me define this graph for you and then show you some interesting facts about it. So we'll define this graph called T of n. It's going to be a graph that's supposed to, every vertex represents one trinomial. So vertex k is shorthand for x to the n minus x to the k plus 1. And you put an edge between two vertices if they dyadically resolve. Now, this definition isn't anything groundbreaking, but the first thing that happens when you come up with this definition is you draw the graph. And when you draw the graph, you see this picture. So here are two of these graphs. This is the graph corresponding to n equals 40 and n equals 100. Arranged so that the vertices are in a circle increasing in counterclockwise order. So vertex 1 starts on the left-hand side. And then
it'd be great for the Valentine contest in my class.
I thought about that. I don't think we had this picture at the time, actually. Maybe, I don't remember, but I thought about submitting it. I thought it would have been cheating, though. Yeah, so the first thing that you see when you draw this graph is there's a big heart staring right at you, right from the middle. Or maybe more precisely, it looks like there's a cardioid, actually. And you see a couple other things. If you look around the ring of the vertices, it kind of looks like there's a circle. Of course, the vertices are arranged in a circle or an ellipse, some kind of circular thing. But I mean, it really looks like there are edges around the circle. So maybe there's like literally a circle in the graph. And then it's a little harder to see this. Maybe if you tilt your head, you have a better chance to spot it. It looks like there's some reflectional symmetry and that you can reflect the graph over the horizontal axis, and it looks like it would be the same. None of what I just said is obvious at all from the definition. We had no idea at the beginning if any of this was real, why it should be there, whether it was there in every graph, but it's the first thing that shows up when you start to graph it. Okay, let me tell you a little bit more about this problem in some of the questions.
And for every n, do you have such nice pictures, or you cherry pick these ones?
For every n, we have such nice pictures, and for bigger n, the picture is nicer. Yeah, that was the amazing thing.
But it's similar. For T41, we're very similar. It was this. The
there does not seem to be any big discontinuity, I think.
They're beautiful.
But it's a good question. That is a good question, actually. How different can they be if they're off by 1, for example? Okay. So let me tell you the first question again. The first question that we asked is, when is the resultant of two trinomials a sine power of 2? When do they dyadically resolve? Another way to ask that is to say, what are the edges of this graph? That's also what we're trying to do. Now, I told you what the edges are. The edges have a definition, but how do you predict in advance what these edges are? So there's an algorithm to compute resultants. You just compute a determinant, but it is not so easy to use this algorithm to come up with any information about when this would be a power of 2 or not. It's not that kind of algorithm. It's not one that you can follow it through and easily derive a formula. Here's a matrix of all the possible resultants that you can compute when n is equal to 10, when the degree of the polynomials is 10. So it's a 9 by 9 matrix, and you see a bunch of different kinds of numbers in there. You see some zeros, some ones, some threes, 31s, 9s. But remember, what we're trying to do is we're trying to pick out the powers of 2 in this matrix. So can we find any patterns in the powers of 2? So if you look here at this matrix, I think you would be slightly misled because at first glance, it seems like it's almost all powers of 2. There's some interesting patterns. Maybe there's some regularity where powers of things that are not powers of 2 crop up, but it seems like if you just pick 2 random ones, then you would think it's probably a power of 2 there. But that is actually not the case. It's hard to see this on a 10 by 10 example. So let me show you a bigger one. Let me show you a 200 by 200 example, which will be a little harder to read, but let's see what we can do. Okay, this is a plot of the adjacency matrix for the 200th graph, when n equals 200. What I mean by that is this is a 200, okay, essentially a 200 by 200 matrix where there's a yellow dot on the screen if there's an edge between 2 vertices, and there's a purple dot on the screen if there's no edge between 2 vertices. And what I want to point out, at least for now, is that there's a lot more purple than there is yellow. So you were a little misled if you thought it was mostly powers of 2, because actually it becomes fewer and fewer powers of 2 as a proportion of all the possible edges, all the possible entries as you get bigger and bigger. And of course, if you look at this, you see lots of other interesting things. There's this very strong diagonal, main diagonal, or it's not the main diagonal, it's kind of the off diagonals. There's this huge cross right in the middle of the screen. There are various slanted lines going from the top left to the bottom right. And there's even a line going from the bottom left to the top right, if you look at it. So any answer to our first question would be something that classifies what all the different things you see going on here are, if that's possible.
Can you predict the Valentine path from the matrix?
Yes, we can predict that. That is one of these slanted lines. I don't remember which one now, but it's one of the slanted lines. That's a great question. It turns out there's a well-known way to construct a cardioid using lines like this, and you can prove that the right lines are there. So we can explain what some of these things are. We know why there's some symmetry. If you look over about the identity line, the y equals x line, there's clearly some symmetry there. We can prove that. We know what some of these lines are, but to be honest with you, we don't know what everything here is. We don't know what all the lines are, what all the points are, if there's families, if there's infinitely many families. We don't really know what happens if you change 200 to 201. We have some rough indications, but we're not entirely sure what's happening here. But as to the density, the proportion of powers of 2 versus not powers of 2, we can tell you that it's a little more dramatic than anything I've said so far. This is a plot that tells you, let's see, what's the right way to put this? The proportion of pairs of trinomials that dyadically resolve. In other words, it's like the edge density of these graphs for different values of n. So if n is kind of small, like around 10 that we saw in our first matrix, it's a decently high proportion. That's what the red line is. It's 80%, 75%, something like that. But as n gets to be bigger and bigger and bigger, the proportion of powers of 2 in these matrices shrinks seemingly down to 0, as far as we can tell. Now, this plot has some other information in it. The extra information that it has at the top, you'd be forgiven for not even noticing it, that it's up there. There's actually a blue line towards the top of the plot as well. That's the proportion of trinomials that are relatively prime, which is a little different than dyadically resolving. So being relatively prime means that your resultant is not 0. That doesn't mean it's a power of 2. It just means that it's not 0. It could be 3 or 5 or 7 or whatever. So if you dyadically resolve, you automatically become relatively prime, meaning that the blue line has to be on top of the red line, but there's no reason for it to be so far on top of the red line. That seemed to be a bit of a mystery. So we don't know how to explain exactly how fast the red line goes down to 0, or indeed if it actually goes down to 0 at all. But we do know how to explain why the blue line is so high. So there's this interesting little fact about trinomials that goes like this. If you have two trinomials of this form, and they are not relatively prime, then they have to satisfy certain very stringent conditions on their parameters. The degree of the trinomials has to be even. So if n is odd, they're all relatively prime, in fact. But the degree has to be even. The difference in their middle exponents has to be divisible by 6. And then, in fact, their GCD is the product of certain cyclotomic polynomials. It's cyclotomic polynomials whose orders are a multiple of 6 particular. Not all of them, of course, but some set of them. And if you take this result and you play around with it a little bit, you can put some lower bounds on how many pairs of trinomials are relatively prime. And it turns out it's about 97% if n is large enough. And that's why the blue line was so close to 1 at all times, because for n big enough, it can't drop below 97. Like I said, we don't know why the red line goes down so quickly. We don't know why there are so few dyadically resolving pairs, but we can at least explain one part of the picture. Okay, and to give you another indication of how hard this might be to answer, the obvious idea that you would try, that I encourage everyone to try if you get interested, is to come up with a formula for the resultant of two trinomials. You could sit down and start trying things, and you'll make some progress, but inevitably you get stuck at various points. And let me try and explain one possible place you might get stuck to give you a sense of how hard this could be. Here's the resultant of two trinomials. They both have degree 900, and then their middle exponents are 22 and 72. You just type this into your computer, you ask it to compute it, and it spits out some huge number. And any formula that you create for this resultant would have to, in some sense, explain where this number comes from. What sequence does it belong to? What kind of family? How do you get it? And it turns out that this resultant belongs to a special class of resultants that we do know how to compute with a formula. And that formula is a little complicated. It looks like this. If it turns out to be the case that the difference in the middle exponents divides the degree of the trinomials, then their resultant is the product of certain cyclotomic polynomials evaluated at 2, then raised to a certain power, depending on the middle exponents. So this specific resultant is actually the 5th cyclotomic polynomial evaluated at 2 times the 25th cyclotomic polynomial evaluated at 2, all squared. So based on this, it's our feeling that any formula for the resultant that you might come up with is not going to be very simple. It might be simple in some number theoretic sense in that it's not insanely complicated. You can write it down, but it's not going to be something like I plus j squared. It's going to be something a little more complicated involving some number theoretic properties, we would say. We do know a couple other formulas for resultants, but they're either just minor tweaks on this one or kind of uninteresting, like barely even that relevant, I would say, for knowing what's going on here. But we would love to know more. We'd love to come up with more formulas for this resultant, but we don't know just yet what's going on. Okay, so that was for question 1. Let me tell you about the second and third questions now. So questions 2 and 3 were asking, how can you find large sets of dyadically resolving trinomials with a fixed degree? And another way to phrase that in terms of the graph is that we are looking for cliques in the graph, complete subgraphs. And what's nice about this perspective is finding cliques is actually much easier to do than brute force. We have faster algorithms to find maximum cliques than just looking over all possible subsets. So if you did some brute force approach, if you had n vertices, it takes something like 2 to the n time to find the biggest clique because you have to look at all possible subsets. But the best algorithms we have for this run in time like 2 to the n over 4 or something like that. So it's a lot easier to find maximum cliques once you phrase things this way. In fact, the hard part computationally in working with these things is not finding the cliques. The hard part is in constructing the graphs. That's what takes a long time. Once you've constructed all of these relations, once you've computed all the relevant resultants that you need to do, finding the maximum clique, empirically anyway, has been almost instantaneous. Whereas for n getting to be relatively large, it can take hours and hours and hours to compute even a specific graph, one singular graph. So if you just wanted to be able to find big cliques, that's pretty straightforward because the clique algorithms are good. But let me tell you a little bit about the cliques themselves of these graphs. So here's a plot of the clique number for each of these graphs up to about n equals 3000. The clique number is the size of the biggest clique in a graph. So this is as big as of a set of dyadically resolving trinomials as you could possibly hope to have in any fixed graph. And what you notice is that it starts off small, very quickly gets up to about 9, 7, 8, and 9, and then it stays there for a long time. Every n here is a single point. So even though it looks like those are solid lines at 7, 8, and 9, those are actually just many, many n's clustered. So they sort of bounce around between 7, 8, and 9 from n equals 500 up to about 3000. You do notice there are exactly 4 points where we go above 9. Yeah, there are 4 points at 10. But for the most part, it looks like the growth of the clique number is extremely slow. When we first made this plot, and even now looking at it, you almost want to say, maybe it's bounded. Maybe it just can't get to be any bigger than 10 because of how slowly it's growing. But this is actually not true, it turns out. The clique numbers do go off to infinity. And what I mean by that specifically, let me be precise. I want to say this. For any fixed lower limit, any number, any integer that you pick, 7, 8, 9, 100, whatever, there exists an n such that the clique number of these graphs will be bigger than that limit for a sufficiently large n. So what I mean is that even though this graph right now seems to be stuck at 10 and below, eventually, if you go out far enough, it will always be above 10. There will be no graphs with clique numbers below 10 at some point. But good luck trying to find when that happens, based on how slow this takes to grow. So at this point,
so we have log n and log n, roughly.
I will tell you an upper bound, but we do not think it's a very good upper bound. So to give you a sense of how long it takes to find this at this point, I think I totaled up all the time that we spent computing this data a couple of days ago. I think it was 10 years of processing time to compute all this data. At this point, every n further that we go, so we're nearing 3,000 now, takes 7 or 8 days.
You only started doing it a few months ago. How can you have it 10 years?
Well, we have
clusters.
We have a parallel program that's running that the people of Canada have been kind enough to donate a lot of processing time to our work. I think overnight at some point, I don't think I mentioned this to you, Eugene, actually, the cluster had given me 3,500 cores at a time. I thought that was outrageous. They should have expelled me from the country, I think, at that point. Yeah, so we have big computer clusters here at Dartmouth and up in Canada working to compute these clique numbers and construct these graphs. And every additional n at this point where we are now takes 5 hours real time and a couple of days CPU time, 6 or 7 days, something like that. So it's, we'll get some more data, but we are reaching the threshold of what is possible, I would say. So our proof of this theorem, in kind of a nice fact, is that our proof is constructive. We can actually write down what the cliques will be in these graphs. So what I have here are a list of sets. Each of these sets is a clique in the graph as long as n is bigger than the largest thing in the set. So the trinomials corresponding to 1 and 2 are always adjacent. The trinomials corresponding to 2, 3, and 4 are always adjacent as long as n is at least 5. 12, 15, 16, 18, etc. Those are all adjacent. They form a K4. So we can literally write down what the cliques are. The problem is that our construction gets very, very big, very, very quickly. It gets so enormously big so fast that it's completely useless for computation. Even already here, the last clique that you see, that's a clique of size 6, but it says that you need to have trinomials of degree 48.4 million or something like that for this to even be potentially useful, which is useless for us. And it's useless in 2 ways. A, it's useless in that you can't use it, and B, it's also useless for predicting when these cliques actually happen, because the first time there's a clique of size 6 happens at degree 22. So you definitely don't need to go out to 48 million. So this proof anyway, proves that the graph gets pulled up off to infinity eventually, but it's a very, very slowly moving infinity. We don't know if it's log n, log n. We'll have to turn our proof into a lower bound at some point, but it's not a good one. So we have some limitations so far in what we actually know about the growth of these clique numbers. So here's a table that tells you for a given clique size, what is the smallest degree that produces a clique of that size. If you just look at the first couple of rows, you start to convince yourself that you can spot a pattern. You see 5 times 2 is 10, 11 times 2 is 22, 41 times 2 is 82, but then the pattern becomes a little unusual after that, because there's this enormous jump at clique size 10 from 82 up to 1668. That was the first dot of size 10 in the plot before. We have not yet found a clique of size 11. The smallest clique of size 11. We know there's a clique of size 11. We can write it down. But we don't know when the first time that happens is. We do know that the degree has to be bigger than 2,985. And probably has to be bigger than 3,000. But we haven't finished running those computations just yet. In fact, it took us so long to compute the smallest n for size 10 that while we were waiting, we decided to prove a theorem about these things. And that theorem is an upper bound for the clique number. So the largest clique in Tn has size no larger than something that's essentially logarithmic. It's roughly like 2 times log base 2 of n, except there's an adjustment factor where you need to think about how many times 2 divides n, where our upper bound is a little tighter than it is generically. So this answers your question, Drone. We have an upper bound that's logarithmic, essentially, but this is a very bad upper bound because empirically it's a lot slower than logarithmic. Yeah, and hopefully we'll find 11 soon, but I'm no longer confident that we will find 11. Okay, so how do we actually prove this coloring? It's kind of interesting. It turns out to be a graph coloring proof. So there's a well-known fact that if you have a clique of size k, and you can, let me say, just for everyone, in case you don't know, a vertex coloring of a graph is a partition of the vertices of a graph into colors such that no 2 vertices of the same color are adjacent. They're not allowed to touch. If you can vertex color a graph with k colors, that means that the cliques in that graph cannot be larger than size k. Because if you have a clique, then you need to have at least as many colors as there are in that clique. So cliques can't be bigger than the number of colors. So what we were able to do is actually find a coloring for our graphs of exactly the right number of colors that I stated in the theorem. And what's kind of nice for our seminar is that we found it almost purely experimentally, just by looking at the output of some data and making some guesses. How we did this is we wrote a program that generates these graphs, and then there's a Python library called NetworkX that can do graph coloring for you. It doesn't claim to do like the best coloring. It doesn't like compute the chromatic number or anything, but it does greedy coloring. So what we did is we just fed it different graphs and said, give us some colors and see what we can find. So if you feed the n equals 30 graph, you get these colors. And if you start to look at them, you see some pretty obvious patterns. The first color is very clearly the odd numbers up to 30, 1, 3, 5, 7, 9, 11, etc. The next one is 2, 8, 14. That's 2 mod 6. The one after that is 4, 10, 16. That's 4 mod 6. And then, okay, 20. Well, then the pattern kind of breaks down. But it sure looks like you've got some sort of congruence relation happening here, where you think of things 1 mod 2, 2 mod 6, 4 mod 6, something like that. And that turns out to be the right idea, although you can't see exactly the right idea from looking at these examples. You need to do something. You need to look at some bigger examples and get a little inspired to figure out what the right pattern is. But this is how we found it, just by looking at examples and guessing. And let me tell you a little bit how the proof goes. Not the full proof, because it's a little complicated. But let's compute one resultant for the talk. That's what I'll say. We'll walk through the computation of one resultant, and then we'll never do it again. All right, I want to compute the following resultant. That n should be a 10. Yeah, they should both be degree 10. Sorry about that. I want to compute the resultant of 2 trinomials that have degree 10, and I want to assume that the middle exponents I and k are both odd. So the first thing that you should know about resultants that I didn't mention earlier is that you can kind of compute them using Euclidean division. So you do one step of Euclidean division on these polynomials, and this resultant becomes a difference. It's the resultant of our first trinomial with a binomial, the difference of just 2 terms. Then what you do is you factor out one of the terms from the binomial, and another nice fact about resultants is that they distribute over multiplication, over polynomial factorization. So you can actually break this down into 2 resultants, but it turns out that the power of x doesn't really matter, and it just disappears more or less. And so essentially you get down to this resultant right here, where you're computing the resultant of a trinomial with this power of x minus 1. Now, the only thing I really assumed is that I and k are both odd. And because I and k are both odd, that means that their difference is even. And because their difference is even, that means that x plus 1 divides this power of x minus 1, which means that at some point in this resultant computation, when we started breaking it up over irreducible factors, we will end up computing the resultant of our trinomial with x plus 1. There's only one root of x plus 1. It's negative 1. So you plug that back into the trinomial. And when you do that, you end up getting 3. You get 1 minus negative 1 plus 1. That's 3. Which means that our resultant here is divisible by 3. So it cannot be a power of 2. In other words, this is not a dyadically resolving pair under the stipulations that we've given. And if you reason through this argument a little bit, what that means is that the odd numbers form an independent set in the graph. And how the general proof works to get the full result is you basically repeat this argument, but for different congruence classes. You want k minus I to be even, maybe you want it to be divisible by 4, by 8, something like that. And if you do this for enough congruence classes, you're able to partition the graph into colors, and you can count how many there are, and it turns out to be the right number. Okay, so let's see. Last little things. I wanted to tell you, Daron asked about the symmetries. Okay, let me tell you real quick that some of these symmetries are here. Some things about this graph that you can prove. There really is a cardioid there. It's there for every n. I didn't cherry pick anything. There's a cardioid. It gets more and more pronounced as n gets to be bigger and bigger. There really is a circle also going around the edges. That's really there. That's not very hard to prove. And there also really is this reflectional symmetry. You can reflect this graph and it stays the same. That comes from the fact that there's some identity about resultants. It's not very important. As far as we can tell, there are no other symmetries of this graph. We think it's just the reflectional symmetry and nothing else for n large enough. We don't know how to prove this, but we think that it's true. But that also means there's some limits to how fast maybe you could compute this. But we wish there were more symmetries. But unfortunately, we think there's just the reflectional symmetry. Okay, let me wrap up just by telling you what the open questions are. So as of a year ago, we had all of these open questions. Now some of them have been resolved, but now we have new open questions. The new open questions, as I see them, are we don't know how fast these clique numbers actually grow, but we would love to know. We don't know what the true edge density is of these graphs, but we would love to know. And we don't know a fast way to compute these graphs for large n. Maybe we're doing it as fast as we possibly can, but it would be great if you could do it a little bit faster so we could get a little more data on these clique numbers. And then finally, nothing that we've said here in principle is that specific to the specific shape of trinomials that we picked. We could imagine picking other shapes, seeing other properties, and replicating all of this analysis, getting different graphs. So that's also something worth considering. But for now, that's all I have to say. So I hope these open questions interest you a little bit. Thanks for listening.
Thank you for a great experimental talk with beautiful pictures and beautiful math. Questions. First, I have a quick question. This is beautiful experimental math, but is it useful to actually computing with the Chinese remainder?
Yeah, I can give a comment.
I was going to say, yeah, of course.
1 year ago, we had 5 moduli, and we actually used it in upper layer on the top of very fast modular library, and we outperform standard benchmarks. But when we now have 10 moduli, we have even better. We have examples when we outperform standard optimized GMP matrix multiplication with large integers.
That's
so
nice.
Based on this modular arithmetic. And
it's potentially useful also, not as beautiful.
Yeah, it is useful. No, it is useful because I have in symbolic computation group, I have people who use this for their modular, for cracking up some algebraic geometry problems.
Oh, they are using it now. Okay, I didn't know if we had gotten it to them yet.
Yeah, Eric Schost actually, well, he used it. So first project was with his student. We tried this. So yeah, this is useful. And I had another comment that there is a mystery here, and actually there is no known formula for resultant of trinomials. This exhaustive search, there is no known formulas for even resultant of trinomial and binomial. There is only one very special case, but I believe that Robert didn't show another nice picture. There is relation between those trinomials and binomials of Fermat shape, x to the n plus 1. And x to the n plus 1, it turns out, is a better choice of moduli than x to the n minus 1, which is recommended in Don Knuth's volume. And those are Fermat polynomials, x to the n plus 1, always dyadically resolve. Any pair relatively primed binomials is dyadically resolved. So they are scalable, they produce nice moduli which used, and Fermat-based scheme outperforms Mersenne-based moduli always by this portion which is overhead, because you don't need to compute inverses when you reconstruct. You know them in advance by your heart in closed form.
Thank you. That's very interesting. Other questions?
Have you thought at all about the possibility of looking at polynomials with 4 terms, let's say, instead of 3?
We'll have to double the number of years that we spent working on this.
Well, no. There is actually, Robert. Yeah, no, Robert. Yeah, you can look at a trinomial with a coefficient not plus minus 1, but small integers. This will correspond to pentanomials or whatever. Yeah, and there are some, some facts that we already know. For example, with this approach, if you allow middle term to have small coefficient like 3 or 4 or 5, you can actually produce a pair with predicted number of terms in inverses. Not just pattern in inverses, but you can tweak them so you have, I want inverses with 7 terms, so you can make them. But generally, we don't know any answer about how many they are, and what is the density of those pairs. And we ask around. I asked many people. I just got a reply from Yuri Matiasevich 30 minutes ago. I asked him about, and he says that he knows nothing about this. He cannot direct to where to look at, to see. And yeah, I spent some time with Askold Khovansky, who is author of Theory of Few Nomials.
Yeah.
But after conversation of 1 hour conversation, the answer was that Theory of Few Nomials is not going to answer our questions because we are dealing with remainder sequences. And few nomials, they just explain, topology at large, not details of, yeah.
More questions to Robert and Eugene? Well, Robert, thanks for a great talk. And please email me the slides when you have a chance, and the recording will be available.
Yeah, and thank you, Doran, for very nice students you sent to me to work with me. I'm happy. I'm very happy. We had very productive week 2 weeks ago.
Sure, and Robert found a new guru. That's not nice.
Yeah.
Yes. So see you next week. Next week we have a double feature, Aurora and Pablo. See you.
Okay.
Thank you. Bye-bye.
Bye, everyone.
Bye.
See you.
Great talk, Robert.
Yeah, sure.